we solve the technical issues, we can start the lecture. Today I want to start addressing the ISO26262 standard. In the past lecture we have seen that we have a growth of embedded computers in many applications that could have a severe impact on the life of the user of the system. We have seen a couple of software failures while defining mission critical systems and safety critical systems. So today we can start looking into ways for managing the complexity of safety critical design in such a way that we have a better chance that everything will be done during the production and validation phases of our item, such that we minimize the risk of having somebody getting hurt by malfunctioning of the system the person is using. So what is ISO 26262? Being an ISO stuff, this is an international standard. So this is not just a best practice that is suggested that gather all the knowledge of coming from a certain field. This is a standard. So this is something that you must fulfill in order to be able to sell your products in a certain market. So if you are compliant with the standard, you can sell your product. If not, you can't. What is happening is that the European Union asked for this standard to be applied in any new electronic and electrical component deployed in passenger cars. This means that all the new vehicles that are equipped with more and more electronic control unit, well, they will see each of these electronic control units designed according to the principle of this standard. Okay. If you look at the requests for quotation that are coming from OEMs towards tier 1 suppliers, you will see that there is a chapter of this request that is containing specifications related to the ISO 26262 in the form as the item shall be analyzed according to the ISO 26262 standard. Supplier must provide evidence of the compliance of the process and the developed item to this standard. So this is becoming, that is having a big impact. As we will see in a minute, and in the next lecture, this standard has a strict sequence of steps that have to be addressed during the design. There are techniques that must be adopted, and this could bring to a significant impact to the established design and validation process of a company. Like it or not, you will have to adopt this. So the better you do that, the better it is. Another element that is important to remember is that for the way in which this standard is conceived, this is not something that you can apply a posteriori. Think about what is normally happening when you write a program. You first write the code, and then you add the comments, right? This is more or less what is happening. Well, this is a posteriori code, let's say, documenting of your work. Well, this is not going to apply for ISO 26262. Another example is the quality. You may have heard about ISO 9001 and so on and so forth. This is a standard that regulates the quality of a production process. Typically, first the process is established, and then the quality manual is written. And sometimes the two are not very related. Well, this is not the case. With ISO 26262, you must start adopting the standard since the beginning of the design. And then you have to follow the prescription of the standard through all the process. So this is something that must be used concurrently with the normal design activities. This is very important, as I said, because this standard, if you strictly adopt it, forces you to perform the different design steps according to a well-established way. Then you may wonder where this approach, this process comes from. Well, here we really have the best practice. So the authors of the ISO26262 were the OEMs, the tier ones, the experts in the fields that gathered together, shared their experiences, discussed for a few years, and at the end they distilled a way of designing electronic and electrical parts for passenger cars that is considered to be the best way, the best possible way. Okay? What's the purpose of this? Remember what we have seen concerning the Toyota unintended acceleration case. Toyota was found guilty because Toyota did not adopted the best practice that the automotive industry recognizes as the best way of designing and validating and deploying electronic system. They use the internal rules that are not in line with what it is generally recognized as the best way of doing things. This will bring to the point where if there is a failure and somebody gets hurt, the law will deem you liable of lacking to comply with the best practice. And this is very important because somebody will ask you to pay a significant amount of money for your failures. So where does this standard apply? The ISO 26262 applies to each electrical and electronic system that has to be deployed in a passenger car. If you are designing heavy-duty vehicles, if you are designing agricultural machines, there will be different standards. It will not change dramatically, but other standards will capture some peculiar features of the other type of vehicles that you may have to equip with electronic parts, and so they will contain different best practices than those that are described here, where we deal with passenger cars only. The standard provides requirements for the whole life cycle of an electrical and electronic system. So this is not something that deals with just one phase of the design. We have seen very roughly last time that we have a development flow that is V-shaped, and we have the conception of the system in terms of architecture, then we go down to the definition of the components, then we have the implementation, then we have the validation, and then deployment in the field. These are different steps that, let me say, bring you from the idea to the manufacture. Well, ISO 26262 applies to all of them. It is not just something that you have to take into account for the implementation phase, or something that you have to take into account for at the architecture level phase. This is something that you have to deal with through all the process of starting from the idea down to the final deployment of the system. What's the key element of ISO 26262? The idea here is that we recognize that depending on the system that you are designing, you may have faults, and these faults can have impact on the well-being of the user of the system. Then not all the systems are the same. Think about the electronic system that is responsible for turning on or off the lamp that you have inside the cabin of your vehicle, the courtesy lamp. well, if it is working, well, it will maybe help you in looking for the key of your house. But if it is not working, nobody will die. Think about the steer lock system. If that is not working properly, it could happen that the steering wheel is locked while you are driving your car. In that case, we will have very bad consequences out of that. Both are electronic systems. Both can be subject to malfunctioning, but the impact of malfunctioning in one case, the courtesy lamp, is negligible with respect to what you will have if the similar malfunctioning, so a broken resistor, happens in the steering lock system that forbid your steering wheel to turn. Okay? So the ISO26262 provides you a method for understanding how severe faults are in the system you are designing. Then, once it is clear which is the level of severity of failures there, we can apply different type of techniques to prevent failures to manifest itself in such a way that nobody will get hurt. If the courtesy lamp is not working, who cares? You don't have to do nothing there. You will easily recognize that it is not working because when you turn the light on, it is not working. Nobody will die out of that. You just have to change the lamp and everything is correctly working again. So you don't have to spend extra money while designing that part of your electrical equipment of the vehicle to guarantee that the courtesy lamp will work always. On the other hand, when you design the steering lock system, you must spend money to guarantee that the behavior of that system will be always safe. That is, we will never have the case that the steering lock enters functioning when the car is moving. As we will see later on, depending on the possible effect of a fault in a system, you could have to spend more when designing that system to prevent the fault to occur. Well, this is extra money that you have to pay. You have to pay extra money for designing the safety features, as we will learn. We have to pay for manufacturing a system with extra components or extra functionalities that are not intended, let's say, for blocking the steering wheel. These additional functionalities are intended for avoiding to block the steering wheel when the car is moving. Okay? This is something extra that is not strictly necessary for just enabling the locking of the car when the key is not inside the car. Okay? So we are willing to pay for new things only when they are really needed. How can we understand when additional features are needed or not? This is an important issue because if we fail in discovering that something is critical and we need to add something to avoid failures there, you may risk to kill somebody. The other hand, if you think that everything is critical, you may end up spending more money than what is actually needed. And so you will soon be out of business. So ISO 26262 is very strong on this. It provides you a method for understanding how critical a system is from the safety point of view, so that you have a clear indication of what you have to do to make that system more robust against possible failures. The concept is conveyed through automotive safety integrity level. This is, let's say, a metric that is used to quantify how much critical a certain system is from the safety point of view, so that we know precisely what we have to do to attack this system. Associated with the ASIL of our system, we will have procedures, techniques that are suggested or must be adopted according to the standard to reach the safety level that the ASIL is asking for. As we will see later on, we have different flavors of criticalities, different levels of automotive safety integrity. And for each level, the standard will prescribe which are the techniques that we have to use when specifying, designing, and validating our system. As we will see, the more critical the system is, the more we will have to spend in conceiving, designing, and validating the system. Then, what's the focus of ISO 26262? Well, the focus of ISO 26262 is the functional safety. This is difficult to understand if we stick on this slide. I had to put here because that is the definition of functional safety out of the standard. But we can have, I think, a better understanding of what it is looking at this example. Think about this scenario. This is an overpass, okay? We have two roads that intersect. We have a road here that is used by the airplanes to go to the terminal after landing. And then we have another road here that is used by the cars circulating around the airport, okay? So this is a crossing because we have two roads that intersect. But this crossing is implemented using the underpass technique. So we have one road here where we have the airplane, and then we have the intersecting road that is located at a different level with respect to the orthogonal street. So what is happening here? It is never possible that one vehicle moving in this direction and another vehicle moving in this direction crash each other. It is not possible. The two roads are at two different levels. We will never have an incident there due to the existence of two vehicles at the same time on this crossing. Never, it is not possible. The vehicle never cross each other, okay? This is an example of a safe system. This is safe. We will never have somebody dying due to the crash of two vehicles on the orthogonal roads at the same time being at the crossing. This is safe. You will never have a failure here that brings you to have an accident. It is not possible. The crossing is safe by construction. No matter what you are doing, you can have the car that here has a problem, and so you have an intended acceleration on one of these cars here. So this goes full speed and traverses this crossing at 150 kilometers per hour. Okay, we will never have a problem when another vehicle is, when this car here is speeding, being in this position. This is safe by construction. Is this clear? Any doubt? Okay. Now, let's have a look at this crossing here. This is regulated by traffic lights. So the traffic light is the function provided by this intersection, by this crossing, that regulates the access to the crossing. So I think that all of us has a driving license, so we should know that when, for example, we have a red light in this way, we have to stop here and the other can pass. And then vice versa, obviously. So what's the situation here? We have a system that is potentially dangerous because it could happen that at any given time, two vehicles can need to cross this intersection, okay? So, in order to avoid harm to the driver and the passengers, we add a functionality to this crossing that is the traffic light. the traffic light provides a functionality that is responsible for guaranteeing that nobody gets hurt when traversing that crossing. This is an example of functionally safe system. If the system behaves correctly, so no failure is harming the operation of the traffic light, the drivers can pass safely through this crossing. This is obtained by an additional functionality, the traffic light. Okay? If the traffic light is not working properly, you can have accident there because there is no functionality that regulates the access to this intersection. So this is an example of functionally safe system. It is a system that embeds a functionality that guarantees the safety of the users. Okay? The other example is safe. There is no particular functionality there to regulate the access to the intersection. It is not needed because the two roads never intersect. Okay? Is this clear? So, the functional safety is, from a certain point of view, can be defined as the way to determine the risk of using a complex system to perform a safety function. The safety function must always work under normal and under disturbed conditions. What does it mean? Let's imagine the traffic light. The traffic light must always work, no matter whether there is an hardware fault in the electronic system that is controlling the color of the light. It must work. Otherwise, if it is not working, it will not guarantee that we never have two green colors on the two intersecting roads, and so we will have the risk of having an incident. So the functional safety is a concept that is related to the risk of using a complex system. Is the system so complex and so important that we have a 100% probability of having a fatal incident out of misbehavior of that system? Well, if this is the case, we have to guarantee that the functionality of our system is always correct. Is the system not critical at all, such that if a failure happens, nobody will get hurt? Well, maybe we don't have to add functionality to guarantee safety there. Then we can say that all the elements that we are inserting in our design must guarantee functional safety. That is, even if we have a fault affecting our system, we do not have an unreasonable risk for the user of the system. We will see later on more in detail this concept, so I hope it will be clearer. Now, we have defined what functional safety is. In 2 words, is an additional functionality we are bringing in our system to guarantee safety, to guarantee that nobody will get hurt by using that system. Okay? This is the bottom line of this concept. Now, let's see how ISO26262 provides you ways for guaranteeing the proper functional safety. This is a schematic representation of the documents that are in the standard. If you go to the ISO.org webpage, you can find the different documents that compose the standard, and you will see that the standard is divided in 10 documents, 10 parts. We have a first part that is the vocabulary. Then we have the second part that is devoted to the management of the functional safety. And then we have the third part that is the concept phase, where we will go more in detail in this course. Here in the concept phase, you will tackle all the analyses that are needed to understand how critical your system is. Based on the result of this concept phase, you will have a specification for the next phases that concerns the architecture of your system, then the development of your system in terms of hardware and software, and eventually the operation of your system. We then have a few other parts. One is devoted to the so-called supporting processes. Then we have the part 9 that provides you some additional details about the procedures to be applied during the concept phase. And then we have sort of guidelines on the usage of the ISO26262 that are documented in part 10. As you can see here, we are referring to a V-shaped development model. This is because the automotive industry since long recognized that the V model is the best suited for the type of activity that are required when developing an electronic system for automotive. So we have a conception of the design, definition of the architecture, design of the components, then we have integration of these components. We have different test phases during this design process, and eventually we have the shipment to the end user of the electronic system that we design. This is again recorded here. We have the descending branch of the V, where we do the specification of the architecture and the design of the architecture and then of the single components. Then we have the testing at the unit level, so we test each component on its own. Then we bring all the components together and we test again. Then we integrate this in our system, and eventually we ship this to the customer. We will have time to go more in details in each of these steps in the near future, so I'm not going to spend too much time here. So let me now give you some definitions out of the vocabulary of the ISO26262. I know this will be a bit boring, but it is needed for have a common language to go ahead with the rest of my teaching. So when addressing ISO26262, we start from the vocabulary. Here we have all the terms that will be used in the standard. There are much more terms than what we are going to see here. These are, I think, the most relevant one. Well, first of all, when we deal with the design of something according to the ISO 26262, we are dealing with an item. The item is the system of array of system of function to which the ISO 26262 is applied. So the item is the steering lock system. The item is the ABS system. The item is the body computer of your vehicle. Okay, so the item is the system or the components inside the system to which ISO applies. Then the item must be analyzed. So we have to investigate on what's the purpose of this item. And in particular, we have to understand what happens if the item fails. For this purpose, the standard defines a few concepts. The first one is harm. The harm is defined as the physical injury or damage to the health of people. The steering lock blocks while driving. We are driving at 80 kilometers per hour on a road with plenty of bends, so we are not able to follow the road. We go off-road, we hit a tree. Okay, so we get hurted. We have a harm there. Okay, then not all the harms are equal. We are driving at 10 kilometers per hour inside the parking lot, and then we do a wrong maneuver due to a fault in one of the electric system of my car, and so I hit another car. Probably I'm not going to get hurted too much there. If I hit a tree at 80 kilometers per hour and maybe I forgot to have the seat belt fastened, maybe I get severely hurted. So the severity is a measure of the extent of the harm to an individual. Are we risking of dying? Is just a negligible scratch on your forehead. These are the type of elements that we have to consider. Then harm and the associated severity are normally the result of a failure. The failure is defined as the termination of the ability of an element or item to perform the function as required. What does it mean? We have a broken resistor. That resistor is needed in the power supply stage of the electronic control unit responsible for braking the car. So that due to that fault, due to that resistor that is broken, the car is not able to brake anymore. This is the failure, the inability to perform as expected. Then, not all the failures are the same. This concept is defined through the risk. The risk is the combination of the probability of occurrence of the harm and the severity of that harm. If the risk is very high, well, the item is very critical. We have to put at work some functional safety techniques, so we have to add functionalities in such a way that we are able to cope with that risk. So that even if the item could break and could stop working properly, we will have ways for mitigating the harm that could result from that failure. If the item is not giving any risk at all because it is not critical for the harm, is not going to create any harm, well, we can do nothing. Then, another term that will be used in what we are about to start looking into is controllability. The controllability could be defined as the avoidance of a specified harm through the timely reaction of the person involved. We could have a failure. So when we press the brake pedal, the car does not respond. So we are not able to reduce the speed of the car. What we can do? if we are reactive enough, maybe we can release our foot from the accelerator pedal and we can operate the manual brake. Okay? This is a way for controlling the situation. This is a way for gaining full control of the vehicle, even in presence of a failure. Depending on the scenario where the failure happens, we will have different level of controllability. We will see later on with a few examples. Then, the last element that we have to consider when defining the risk associated with a failure is the exposure. The exposure is a way for measuring the probability of being in a situation that can be cause of harm if coincident with the failure. When we are able to identify the severity, the controllability, and the exposure, we have all the ingredients to derive the autonomous safety integrity level. So the automotive safety integrity level, ASIL, is a way for measuring how critical an item is, based on the combination of severity, controllability, and exposure. We will see later on that this is a result of the concept phase of the standard. According to the concept phase, we will have to analyze the different scenarios where the item can be used. We will have to evaluate the different faults that could happen during the operation of that item in that specific working conditions. Then for each of these, we will have to guess what will be the severity, the exposure, and the controllability associated with the failure in the item when it is used in that specific working condition and a certain fault happens. Once we are able to do this exhaustive analysis, that is not easy at all, it is not trivial at all, we could end up identifying the risk in terms of ASIL. The ASIL is made of 5 levels. We have QM, that stands for quality measures. It means that the item is not risky at all. If we have a failure there and the item is no longer able to produce the expected functionality, who cares? Nobody will die out of that. It is just a matter of the quality that you perceive out of your item that is deployed in your vehicle. Like having a smartphone that from time to time stops working. It is, let me say, an hassle because you have to reset it. Sometimes you have even to remove the battery to do a hard reset, but then nobody will get out of that. It's just a bad perception on the quality of the product that you are using. Then we have the ASIL level A, B, C, and D. A is the least critical, D is the most critical. As we will see later on, depending on the ASIL level, we will be required to adopt specific techniques during our development phase, during our validation phase, to minimize the risk of having harm due to the failure in our item. The hazard is defined as the potential source of harm. What is an hazard? The hazard is the malfunctioning of the radar that is used in the cross-traffic access system, so that we are no longer able to measure the distance of the incoming object towards the vehicle. So we are not able to tell that is the time for braking the car because there is an obstacle that is hidden to us, that is coming towards us, and we have the risk of an incident. We will see later on an example of this. In general, the hazard is the source of the harm. Once we have enumerated the possible hazard that could affect an item, we can perform the hazard analysis and risk assessment. This is a very important part of the standard. This is something that we will learn to do here. This is something that will be part of the exam. So you will be given with an item, you will be given with a specification of the functionality of the item, and then you will have to perform on your own the hazard analysis and risk assessment. So you have to put at work the techniques that are prescribed by the standard to understand how critical an item is and to propose countermeasures. Obviously, we will need time to learn this. We will start at looking at some examples together. We will do exercises together. Then, once we have completed the hazard analysis and risk assessment, we know how much critical a certain item is. So for this, we have to introduce the countermeasures. So we know that an item is critical. We know that somebody could get severely hurt due to a malfunction in there. So which are the functionalities that we want to adopt, that we want to insert in our item to prevent that kind of severity? So to avoid that the failure produces an harm to the person. Well, this is associated with the concept of safety. Our system is safe, our item is safe when there is an absence of an unreasonable risk in using that item. And the safety is obtained through safety goal. The safety goal is the safety requirement, that is the additional functionality that we want to have in our item that are resulting from the hazard analysis and risk assessment. So the process will be, let's start analyzing the item. Let's start understanding where I can use that item. Let's start to understand which are the failures that could inhibit the item to work properly. Then let's see what is the outcome of each of these failures. Is this something that is very likely to happen? Is this something that when it happens it is impossible to control? Is this something that could kill somebody? Well, we have to take care of that. We have to introduce a functionality such that the failure is not going to kill anybody. Is the failure very, very improbable? So it could happen only if we are driving at night with light off, it is dark, so we have no moon, it is raining and we are drunk. Well, maybe this is very unlikely to happen, I hope. And so maybe we can neglect that thing, okay? Let me look into one thing and then we have a short break. So you can stop talking, okay? It is quite annoying. Please, if you don't want to stay here because you have to, there is sun, you have to tell somebody, to the colleague that you have beside you, you are free to go. The lectures are recorded, so if you don't want to stay here, no problem. If you decide to stay here, please be silent. Even if this little chatting that you are doing is very annoying, because you are more than hundreds, and I am alone here, trying to tell these difficult concepts, okay? So please be fair. If you want to talk with your colleague, that's okay. There is plenty of empty space outside. It is warm. There is a nice sun. It is Friday, so start the weekend earlier. But please, if you decide to stay here, be quiet. Thank you. So here is the important thing that we have to look at to understand which is the chain of event that could happen. So we start with the correctly functioning vehicle not in use. So we have our nice car that is parked in our parking lot. The engine is off, nobody is seated there, okay? So this is the starting condition. Everything is working correctly in our vehicle, even if we are not using it. Then we could have two scenarios. The first one is that we have, due to the, let's say, due to a weak assembly of the vehicle, we could have a failure that occurs. Let's say we have a connector that has not been plugged correctly into the proper socket, and so just out of gravity it disconnects. That is a failure. Let's imagine that the connector is the connector that connects the speed sensor on the wheel of your car to the ABS. So the ABS needs to pick up the revolution speed of each wheel of your car. So there is a connector there. Let's imagine that this connector disconnects for any reason. This is an example of failure. The failure occurs when the vehicle is not in use. Okay? So we change state from correctly functioning vehicle not in use to incorrectly functioning vehicle not in use. So here nobody gets hurt. Okay? Then let's imagine that you enter your car, you do key on, and you have on the dashboard problem with the braking system. So you will not start using your car. You will ask for a service. Maybe you will ask for a truck to come and pick up your car and bring this to the workshop so that it can be repaired. Once the repair action has been done, you go back to the currently functioning vehicle not in use. So here we don't have a problem. Nobody gets hurt because nobody started using the car with the failure affecting the expected functionality of the vehicle. Okay? The other situation could be this one. We have a currently functioning vehicle, and then we start a mission. What does it mean? 8 o'clock in the morning, we go downstairs, we enter the car, and we start driving towards our working place. That is the mission. We drive the car. As long as the vehicle is correctly working, no problem. We are driving safely towards our destination. Then we could have a failure. It is, as I said, we have a loosely connected wiring. During the road towards vehicle, we cross a speed bumper, and the vibration that takes place when crossing that speed bumper is such that we lose the connection. Well, we have a failure there. We have part of the system that is no longer able to produce the intended functionality. The ABS, for example, is not able to read anymore the speed of the right front wheel, the one that was connected to the link that has been detached. So here we have an incorrectly functioning vehicle in use. So we could have an effect due to this failure. Let's imagine that the driver brakes the pedal too much, let's imagine that the road is wet. Let's imagine that the wheels stop rotating immediately. So we have the car that starts sliding. So we are losing traction, and the ABS should start working. But it is not able to work properly because it is not able to measure the speed of one of the wheels of the vehicle. Well, if the driver is a good driver, even if the car is not doing precisely what it is intended for, it can control the situation. So, for example, we can have the capability of parking the car immediately on the sideline so that no incident happens. So here we have the capability of controlling the failure. If this is the case, we can end the mission. So we were able to recognize that the car is not braking as it should be. So we park it on the sideline and we turn off the engine. So we are here in correctly functioning vehicle, not in use. Okay? Other scenario could be the case where the same connection as before is, let me say, subject to an intermittent fault. This means that the connector is there, it is in the socket, but it is not plugged correctly. So depending on the vibration, it can make contact or not. Okay? So if this is the case, we could have an incorrectly functioning vehicle in use, and then due to the vibration, the connector can again make the proper contact. So we have that the hazard is controlled. The fault could be mitigated, and we have back again a correctly working vehicle in use. The bad things happens when we move towards the end of this chart. So let's imagine that we have the hazard. So we have the failure is active. Let's imagine that the driving situation is such that we should have the function provided by the faulty item, but we can't because the item is faulty. So, for example, we are not able to take the desired path out of our car. Example, we are braking, we are losing friction, so we are no longer able to drive the car anymore. So we are in the condition of reduced controllability. The speed is too high, the tires are not having grip with the road, so it's like moving on the ice. The car is going you don't know where, and you are not able to control it accurately. So you have reduced control. If you have good experience, it may be the case that you are able to take the control of the car even if it is not doing exactly what you want. So even if the control is reduced, the reaction of the driver is such that you can go back to the incorrectly functioning vehicle in use. This is a good situation. Even if the car is not going well, you are able to keep control. The last step is this one, moving from reducing control to impossibility to implement the driver intention. This is the case where you have the incident. If the incident happens, we could have severity. So we have harm, somebody can be very bad harmed or not. It depends on the driving scenario. So this is state 6, the state we want to avoid. So our functional safety must put at work all the functionalities to prevent this scenario. So we don't want to have the accident. We could have reduced control, but the functional safety concept should come at work and should allow me to be always in state 4 or in state 2. So if the car is faulty, we must be able to control it anyway, in such a way that we are not going to harm anybody. And we must be able to park it safely. Okay? Any questions so far? So let me have a short break here, let's say 10 minutes, and then we start again with the next part of the lecture.